to the most difficult one. Okay. Okay, today's topic, sorry. The title, how to prove a circuit. How to prove a circuit. So what's a typical circuit? Okay, circuit is like, there are actually two types of circuits. One is the so-called Boolean circuit, another is, the other is arithmetic circuit. So generally we only care about the arithmetic circuit. Saying that here we have, just randomly draw a circuit, okay. Sorry. For each gate, it could be a additive gate or a multiplicative gate. For example, here is a multiplicative gate, and here is a addition. Is a randomly, yeah, okay. It's a circuit, typically a circuit. For each circuit, we'll have two inputs wires and one output wire. So for each circuit, kind of. So generally, we can also support, more complicated gates. For example, in the modern Planck circuit, we can support the polynomial gates and the lookup gate, or even hash gate. So one gate we can do a simple hash operation. So, but in theory, if we support addition and multiplication, we can model all the finite computation. I mean, all the computation with the finite steps, any computation trace. So, okay, in theory. So that means that if we can prove that addition with multiplication, then we can literally put everything that, every computation done by our computers. But I think that the most difficult thing is that how can we prove the circuit without revealing all the values, any values of the circuit. For example, here is a private input, like for example W1, W2, and here's some public inputs x1, x2, W3, W4. We just put the values into the circuit, right? We can get an output deterministically, okay? Yeah, please remember that, okay, here those four values are witness. Okay, then this where should be private, cannot be revealed to the prover, right? And also this where, right? And this where, okay, it's okay to reveal to prover because x1 and 2 are known by the verifier. So, but here, this where should be kept private, right? Because this where is private. So let me use a different color to. Okay. Okay, the black color shows that the where can be revealed, and the blue wires should be protected. Then how to prove a circuit? So then we decompose the problem into sub problems. So how can we prove that one? For example, we have three value. Then how can we prove that A plus B equals to C? Okay, this is our first task. So even now we first try simpler protocol that we prove that, okay, how can I prove this one value equals to 0 if we have the commitment of A equals to, we put it in a box with a, sorry, we use another Greek letter. So tau A is the randomness to protect A, right? If we use the multiplicative notation, we can define the box as, okay, here. In the following, we just use the square bracket notations with multiplicative operation. Okay. So the task is how can we prove that if we have such commitment, we put it on chain or we send to anyone, send it to some people care about the A, but without knowing A. But we can prove, okay, A is equal to 0. So, okay, it sounds like useless, right? Because we prove A equals to 0, then okay, all right. So A must be 0. Why we bother to to prove that? Okay. Okay, just we show that the technique. Okay. Okay, prove the 0. So the protocol is simple. So for example, we have a prover and a verifier, Alice and Bob. So first of all, the prover will generate a randomness called R. So sorry, two randomness R and row R. Right, they are randomness. The purpose of two with randomnesses are for protecting two witnesses, A and tau A. Okay. So we told the prover tosses coin and get R and row R. So make them random. Then the prover puts the two randomnesses into a box, get R, capital R, as we talked before in the extended Schnorr protocol. So first step, the prover just send capital R to verifier. And then the verifier will challenge using some, let me use another letter, okay, E as a challenge number. E from, okay. It's, okay. And then at the third step, the row will compute ZR equals to row R plus E times tau A. And then send the ZR to verifier. Okay, that's all. Then the verifier can verify if prover, to verify if the proof is valid. So the verifier will verify that put 0 and ZR into a box to verify that R times A to C.
To C, because usually the...
Oh, sorry, E, sorry. E. I'm sorry.
That's from the, it's usually previously always had the verifier send back the challenge, right?
Yeah.
Which is now the randomness and the multiplicative final fields?
Yeah.
Okay.
Yes. So, okay, let's use E as a challenge because today we will prove A plus B equals C. So C, we cannot use C as a challenge. So it's simple, right? It looks simple. So, okay. But I still, stop here for 5 minutes.
Yeah, like E is still what we previously had as C, but now we just, like it's the same like before.
Yeah,
but now we just don't use C as the variable.
Yeah, okay. Yes. So So it's very simple, but still, so I just stop here for a couple minutes and then make sure that, okay, you can draw it on your paper or and think of the Schnorr protocol that we discussed before and compare them. Okay.
Question?
Okay.
Can you explain again, like, with the multiplication and the addition gates, and like those values have to do with the equation on the left?
Sure.
Yeah.
The circuit?
Yeah. What does the circuit have to do, or like those specific values that you put in underneath it have to do with the equations on the left?
Okay. Okay. This is protocol only for proof that A equals 0. So in the end, we can prove that the circuit. But right now, we just go for the first step. Just prove the A equals 0 and A put in. Actually, we prove that there's A inside the box, but the box, because we still has a tau A randomness. So the A from outside, which is okay, this is a random number, but is 0 hidden in there. So the goal is that, okay, we'll prove that, okay, there's 0 actually committed in the box. So, okay, sorry.
Are you okay?
I think I should write the formula on the classes. So first of all, we can, yeah. Are you all right? Okay.
It's a good idea.
Lucky then. Yeah.
Yes, like 0 is like at the bottom, like 0 is A, right?
Here? Yes, yes, because because we want to prove that A is 0, so verifier just put 0 here.
Okay.
Yeah. Okay, this protocol looks simple, but it's important building blocks for building large proofs. All right. Any other question? Yeah. 3 minutes. Okay. Don't worry. No hurry.
It's the first time where the verifier checks specifically for the results. I mean,
Yeah.
right? I mean, we just put 0 in there.
Yeah. It's because the theorems, the statement is that, okay, a 0 inside, so let's put a 0 here.
The verifier can just put 0 in there.
Yeah.
Okay. But obviously, normally we wouldn't really do that because, like, if the secret is 0, right?
Yeah. It's for an honest prover, A should be equal to 0.
Okay.
Yeah.
But the verifier should know it's 0.
Yeah.
In this case, he knows it's 0.
Yes. Yeah. This theorem is A equals to 0. Okay. This statement that I want to prove. Yeah.
try to differentiate, because before always the secret was always obviously secret, so in this case it's not.
Yeah, yeah. Okay, 3 minutes left. Okay, let me. Okay, so why this protocol is useful? Because, for example, we have two commitments, A and B. So if I want to prove that, okay, the value inside A is equal to value inside B, A equals B, we just prove that A minus B, there is 0 inside A minus B. So that's why this protocol is useful. Even looks like useless. It's seemingly useless. Yeah. All right, so let's move on to the second protocol. Okay, the goal of the proving system is to prove A plus B equals to C. And the public inputs are A equals to A semicolon tau A, B equals to B tau B, C equals to C tau C. Okay. And prove A plus B equals C. So the verifier only has a capital A, capital B, capital C. Kind of, black boxes. But we'll prove that, okay, the three values hidden in the locked in the blocks is actually they satisfy addition, additive, the relation. Okay.
Is the goal here something that's the constraint, something like that, or not really yet?
Constraint? What do you mean?
Like when you have like the proofs, you define constraint like a
Yeah. Yes.
Is that like
It's similar, yeah. But in modern ZK snarks, we batch a lot of addition proving, you just batch them compressed into one, or But here we decompose the steps
Yeah, just
to make sure, yeah. So how to prove the one addition. Then we can, move on to how to batch them together. All right, so the prover and the verifier. So the verifier has capital A, B, C. The first step, the prover will generate some randomnesses, and RA, RB, row A, row B. So, and another row C. And the prover generates RA, capital RA, and RA, row A, and RB, row B. And capital D equals to RA plus RB, row C. Yes. Yes. The prover generates three commitments: RA, RB, and D to the verifier. And the verifier will reply a challenge E. And then the prover will compute that 5 values. ZA equals to RA plus E times A. ZB equals to RB times B. And E0. The row C plus E tau C. Z tau A equals to R row A. All right, looks complicated. A, the B, the tau A, the tau B, and Z tau C. Okay, 5 values to the verifier. Okay, then for the verification part, the verifier will verify 3 equations. First equation that ZA Z tau A if equals to RA times A to E. The second equation is like the B Z tau B is RB times B to E. And the third ZA plus ZB Z tau C if equals to D plus times C to E, capital C to E. Oh, it's a little complicated. Okay, don't worry. Don't worry. Well,
What is on the fourth Z, no, ZA, ZB, Z tau C, and then Z tau?
which one?
Yeah, this one. Is it Z tau A? Okay.
A Z tau A, yeah. So I'm sorry. Yeah. Okay, take a look at this equation first. The first equation of the verification that actually is saying the verifications for the proof, the verified the knowledge of the small a, right? So kind of this protocol can be, vertically split into 3 different protocols, but actually they are quite tightly closed. But for the understanding that we can say, okay, the first equation for proof that the prover has A. Okay, it looks like a simple Schnorr protocol. And also the second equation. Second equation is proof the knowledge of small b. So but the third equation looks weird. So now let's get into the intuition of why this third equation looks like this. Okay.
Why we don't have the RC?
RC? Okay.
Why we have only RA and RB?
Okay, just we don't need that.
I didn't.
Okay. So, yeah.
Like because we don't need it because we just need to prove that A plus B is C.
Yeah.
We don't
So
need
if
to know.
Okay.
yeah.
The goal, okay.
Yeah, John, you get the point. So if we already proved that A plus B equals C, we don't have to prove the knowledge of C because we don't have to do that.
That is R.
So only thing we prove that knowledge of A, knowledge of B, and there exists some value that A plus B equals that value.
Just like the goal, like this is in the when we have like a computation where we make an addition, right?
Yeah.
Okay, so
Yes.
Okay, so it's like we have a program that is like just adding 2 numbers.
Yeah. So prove the addition. Yeah.
Okay. So if we have like a more complicated computation, this would be like
Yeah.
longer.
Every limited computation can be decomposed of 2 addition plus multiplications. Yeah. Sorry?
In the first protocol, you're missing the proofer needs to send the Z0 or
Z0?
which is R, small r.
Oh, okay. Here okay. You're saying actually okay. The protocol we need another Z, right?
Yeah.
So what's the problem of this protocol if we okay?
In the final equation, on the left hand side, we don't have a small r, right?
Don't have a small r.
In the final equation. But on the
All
right
right.
side,
All right.
small r, so it's not equal.
Yes, we don't have small r. And yeah, okay. A simple homework for you. So you can write your own protocol. Then in the end we can compare that. Okay. So if you just okay, you give me your version of the protocol of proving 0. Okay. So if here we have another Z. So what the difference is between this version and your version? Okay.
I mean the
Oh, it's not equal. Okay. All right. All right. All right. Okay. Thank you. Let me check. Yeah. Yeah. Here. Sorry. Here should be R. Am I right?
No.
No?
It's just send
Yeah.
0 point.
Okay, I see what I'm. Yes. Okay, good point. Good point. Yes.
The power of G is not equal.
Sorry?
The power of G is not equal.
Yes. 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 Shall I put R here? I think. All right. No. Okay, we need to send another. Yes, you are correct. Sorry, your name? Oh, yeah. Can you correct my version? Okay, thank you very much. I need more Z, right?
Yeah.
Okay.
So yeah, I think that we should change it into Z tau A. Z tau R for this.
Yeah.
A for this, and is Z for A, and equal to is the A P R, and is the R equal to A, and yeah, because A equal to 0, so it's R, and we send this yeah, like this. And yeah, we prove that this
Okay.
zero is the R and the
Tau A.
tau A.
Okay. And ZR. Okay, here is ZR, right? Z or ZR. Z. Okay. Okay.
Yeah.
Okay. Okay. Thank you. Thank you. Good job. Okay, let's back to the second protocol. So don't trust, verify. Okay. Okay.
Sorry, the ZA equal to what's the first pair? R. Oh.
Here?
No, the prover.
Prover.
Yeah, ZA equal to R.
Yeah, R. Yes, R. Yes. Yeah, here is rho R. Yes.
But ZA equal to R.
Because A is 0, so yeah.
The notation is there is just C here first. Oh,
ZA, okay, you can use Z. Okay. Yeah, it's fine. Okay, here. Okay, first of all, check if the an honest prover check the complaints of protocol. I ask your help. And then, okay, let's stop here for 5 minutes. Check that. Okay, don't trust me. Is that correct? Okay.
Yes.
You verified?
Yes.
Yeah, okay, good, good. Okay, the basic intuition of why we use the third equation to verify, here is the point that always we have the Z, right? Letter Z. We view them as the encrypted witness, right? By using a randomness as a key and also a challenge from the verifier. So Z, literally we can say, okay, they are encrypted data. So what if, if we want to prove that A equals B equals A plus B equals C, so how, first of all, we try to prove the encrypted A plus encrypted B. And see, okay, what the result is. So we just add ZA plus ZB to see what will happen. So ZA is the RA plus E times A, and plus RB plus E times B. And then we get the RA plus RB plus E times A plus B. Okay. And then if for an honest prover, so ZA plus ZB will be equal to this one, right? Then, so in order to allow the verifier to verify this equation, so we have the prover has to provide enough the elements to allow the verifier to verify the property. So because the verifier cannot see the witness value, so the prover should provide enough elements by using the commitment scheme. So the RA, RB, and RD, actually the D here is for provide a very useful element for the verifier to verify this equation. So then the verifier can, just like FHE, the idea that, so the verifier cannot see the hidden values, but still the verifier can verify the addition of two encrypted values. So let's say, for example, D is we commit RA plus RB into D to make sure that, in the end, the verifier can have this one, but in the box, put in the D. And A plus B, A plus B, A plus B already in the box because A plus B is in the capital C. So now the verifier already has a box with RA plus RB inside and a box with RA plus B inside. But the annoying things are left that we have to deal with the blinders or the randomness. This part kind of annoying. But we have to deal with that to make sure that the blindness still satisfies some equation. To make sure that the verifier can verify both the witness and the blinders are satisfied with some relation. Then let's say the blinders for ZA plus ZB. ZA plus ZB. So blinders for because ZA we use RA and A to encrypt to get ZA. The blinders are so blinders of RA is row A. So the blinders for RA is row A. The blinder for RB is row B. Then for A plus B, the tau A and tau B. Then if we have for example, this box actually is a real D, right? D, not D. It's because D we have to generate additional randomness to protect RA plus RB. So we'll have a very strange RC to protect RA plus RB. So now we have to make the equation balance, for both sides. But fortunately, we can use the RC as the key to protect tau C. We can get a Z tau C. And luckily, we just put tau C here to make sure, the equation holds. We can check that equation to expand the definitions to see. Let me. All right. So for the verifier will in the future, for example, in the future, verifier will put ZA plus ZB in a box to homomorphically verify the equation. But right now we don't know what should put here. We just leave it's blank. Okay, leave it blank, and then construct the right-hand side of the equation. Here D is the main ingredient. Sorry, how to say that?
Like
Ingredient, yeah. Thank you. So they put RA plus RB here, and rho C times box. So the box, the value part of the commitment should satisfy this equation. So, but the blindness part, we should make them balance. Use something, dirty. Here we have the C, the box here, because C equals to A plus B, so we put A plus B here, and tau C. Okay. Sorry, put E, right? Okay, in order to make the equation hold, then it will be clear that here should equal to RC plus E times tau C. Okay, we just gave it a name, Z tau C, okay. So we'll give it a name, Z tau C. Okay. Yeah, we got it. The equation. Yeah, so proving the addition, okay, it's not so hard. Okay. It's not so hard. So here, any question?
Yes.
Okay.
So it means that rho or C needs to be
This one?
Z of tau C.
Oh, Z tau C, okay.
No, rho or C on the prover side on the first step.
This one?
No, the rho C here. So this
Okay.
needs to be Z tau C.
No.
So
Rho C is for protect RA plus RB.
Okay.
Because the verifier needs this
okay,
part,
okay,
so
okay.
the prover has to commit this part. But in order to keep the secret, keep the privacy, we still have an additional randomness to protect RA plus RB. Then, at the third step, prover need to send something to make sure that the verifier can verify the equation. So, yeah, first of all, we just leave that as blank. For example, to design a new protocol that, okay, we don't know how to put it here, we just leave that blank and write the whole equation, and then, okay, we make sure, okay, the blind should be this one, that everyone will be happy. Okay.
So this last equation on top, we have like
this one?
Yeah, this one. So this one with the additional randomness to secure the prover is the one below that. I mean, because like the randomness A plus randomness B. Yeah, exactly.
Okay.
Plus E times A B, right? That
Yeah.
we can. The prover knows this, but the verifier, we have to add new randomness to protect the prover. So that's how we get from there to the equation below that, right?
Yeah. Okay, please say that again.
So now I was just confused how we get from this equation.
From equation to this equation.
Yeah, exactly.
Okay, I see.
It's just with the added randomness to protect the prover. With the, I forgot how to say the added randomness, not the P. I forgot how it's called.
Okay. First of all, for every commitment, sent to verifier should be protected by some randomness. And a new randomness, we cannot reuse the randomness, right? Every time we put something in box, we need a new randomness. Okay, the first principle. The second, the verifier should verify. So just we just remove the blinder part to make sure that the verifier can verify the left part of the left component of commitment. So because the verifier has the two encrypted data, so just add them together. Then we'll have the formula like this. So if to let the verifier verify this equation, so the verifier has no value of this one because the two randomnesses are secret, cannot be known by a verifier. But we can have a commitment of the two values, the sum of two values, the RA plus RB. So then, while in the first step, the prover has to construct a D to commit it to RA to RB, such that the verifier can verify Z plus ZB equals to, okay, here is a new commitment from the first step, and this is a commitment, part of a commitment of box C, capital C. Then, at least for the left component of the box, the verifier can verify the equation. But for the blinders, the prover needs to send more values to make sure that the verifier can verify the blinder part. So for how to come up with the protocol, we just leave the blinder here as blank and to calculate. Okay, Leo.
James, in general, we're using two kind of encryption, not the box and the set.
Yes.
I'm using the set because those have the homomorphic.
Yeah.
And the box doesn't have the homomorphic property.
I think. Okay. I don't know.
Yeah, we could, to calculate the set, we could use like the box, like the hashing, the transition. We could use, yeah, or why to the, yeah, we don't know.
Yeah, probably I have to stop here for a couple of minutes because proving a multiplication will be more complicated. Yeah, 3 minutes. Okay, 3 minutes. Okay, all right, Kiba.
Quick question. So, like the last results that we derived in the last equation.
Okay, here.
Yeah. So I get that we needed to derive it to prove that the circuit works, but isn't that same value also passed by the prover to the verifier in that last sequence as well? So, like the very last one on the second base, yeah. Isn't that the same value that we derived?
Okay, here is the third. Third.
So basically we derived it, which is what the prover would do, and then he says, okay, I would need to have this value in order to like complete the proof, and then that last value is also provided. Okay.
Yeah, correct. Okay, 1 more minute. All right.
So in the second phase that we are generating the proof, so C of A and B is for generate proof of the two elements, the
Yeah.
And for the tau itself, like the tau A, tau B, these one for checking that if they are really random.
Yeah, the random also witness. Yeah.
And for the, I'm not quite sure on the tau C, that what is purpose for? What is purpose of the
Tau C.
Yes, the proof of tau C.
Okay, here Z tau C or tau C.
Z tau C.
Z tau C. Okay, Z tau C is to make sure that the balance of this equation. Yeah.
Okay. Because if that one is losses,
Yeah.
cannot prove the right side.
Yeah.
Right,
Yes. Yes. Yeah. Yes. Okay. Warning here. So that's all my understanding. So on the textbook, nobody explain why this protocol works. So don't trust me. Okay.
Yeah. I think the disclaimer.
Okay.
Because it's kind of weird a little bit.
All right, let's move on to the third protocol. Okay, to prove A times okay, the goal is to prove A times B equals C. Okay. Are you ready? Now let's go. Okay. First of all, the public inputs are the boxes of small ABC. Okay. A, we have a tau A to protect small a, and B. Okay, now I have prover and a verifier. Okay, the first step, the prover will calculate the RA equals to new randomness. Okay, randomness. We'll have the row A, row B, epsilon 0, epsilon 1, I think. Yes. Yes. Prover will calculate RA equals A row A. RB equals to RB row B. And capital E0 equals to RA times RB epsilon 0 and 1 equals to A times RB plus B times RA. The first step, the prover will send the verifier RA, RB, E0, E1, and then get the challenge E from P star, and then, okay, ZA equals to RA plus E times row A. ZB equals to RB so row B. And Z tau A equals to rho A. Z tau B equals to RB times B tau B. And Z tau C equals to epsilon 0 plus E times epsilon 1 plus. Okay, all right. This rewrite a bit of ZA, ZB, Z tau A, Z tau B, and Z tau C. Okay, to the verifier. Okay, it's all right. Okay, it's not too complicated as you think. Now, verifier will verify only three equations. Put it here. First equation is that the ZA semicolon Z tau A, if it's equal to R times A B, and ZB Z tau B and ZA times ZB semicolon Z tau C is equal to E0 times E1 to E times C to E2 squared. Okay, that's it. Okay, most mysterious equation is the third, right? Yeah. Let's find more space. Yeah, the idea is similar. The idea is similar. So, because the verifier has Z and ZB, so verifier can multiply them together. The AA plus times ZB equals to the RA plus E times A times RB plus E times B, right? And then we expand the multiplication. We got RA times RB plus E times A times RB plus B times RA plus E squared times A times B. Okay. If the verifier wanted to verify this equation, over here the verifier needs the commitment of this one, right? And also the commitment of this one. And above here, C, capital C, right? Capital C. But then the prover has to commit two values in the first step. So then that's why we get E0 and E1 here. And E0 is the RA times RB, and E1 is for cross term, kind of cross terms. A times RB and B times RA. And we still need 2 more randomness to protect the commitment. So we got a new the epsilon 0 and the epsilon 1 here. Then we need to make the equation balance. Okay.
Is ZA and ZB correct?
Yeah, it's like
I think it should
below A
be
or B.
E dot A and
Oh, sorry.
On top of the board on the right.
Oh, sorry. Oh, where? Oh, okay.
Yeah.
Okay. Yes. Thank you very much. Thank you.
Like R is the random.
Yes. A, yes. So, yes. Sorry. Yeah, here's A and B, right?
Yes.
Okay. Thank you. You're great. Awesome. Okay. Anyone verify the completeness of the protocol? I'm afraid of making another mistake here.
Yeah,
Correct.
But the verifier is also the RA plus A, RA, RB. First one and second one should be the RA and B.
Okay, here?
No, the verifier should be RA.
Oh, yeah. Thank you very much. Yeah. Yes. Now let's make the equation, balanced. Okay. The verifier have to put the A times the B here, and then leave the blinder blank, and equals to that. The commitment of RARB is E0, right? E0 times, here is the E1 to E, and C to E squared. And then we extract the blinder out of it. E0 we got epsilon 0. And for E1 we got the blinder epsilon 1. And for C, the blinder of capital C is tau C. Right? So then we can fill it out, the blank out, with epsilon 0 plus E times epsilon 1 plus E2 square times tau C. Okay, put it here. Then finish the protocol. Okay.
Okay, so I understand the breakdown and kind of like getting back to the ZK circuit. So basically we have one computation and we break down that computation into addition and multiplication.
Yeah.
And then we prove all of them individually. And
individually.
And then the out is then the entire proof, or?
Out can be a poly input or not, or still a blended value. Yeah.
Okay.
Yeah, for a circuit now we can prove the circuit. We literally commit everywhere. Right?
Out can be but what is the purpose in out again? Like we've proved the circuit and out is just whatever we want it to be, or
yeah, or yes, probably
like
it's kind of a Boolean 0, 1 or something. It depends on the specific circuit, the circuit that is defined. Yeah, it's not practical, but now we know how to prove a circuit, right? Okay, those techniques were popular 10 years ago, before the modern ZK came out. So actually we'll have more techniques to aggregate or batch of the commitment is kind of a number equal to the number of the wires. Kind of if the circuit is 1 million gates, could be totally impractical to prove that. But now we have some techniques to aggregate them together. But we won't go that too deep. And tomorrow we will prove a little bit more complete relation, like an inner product. So if we know how to prove an inner product, then we will know how to prove a polynomial evaluation. So we'll get closer to polynomial commitments. Okay, we stop here for 5 minutes for you to write down paper and to review that, to compare the 3 protocols. And for any of you interested in this lines of work, actually, I think from the early 90s to 2010, before the Pinocchio Group 16 came out, there are a lot of papers about those techniques. Actually, there are a lot. And I think I recommend the Damonet's book. I don't remember the title of the book. The link is in our DC channel. And if you are interested in lines of work, just check it out. And but personally, I saw a lot of techniques inside the modern snarks, many different constructions. But I can see that techniques are used, implicitly, many places. So kind of, but I think it's these techniques are just the beginner friendly, and I can understand the basic intuition. But it's still this is a little bit far from the modern star constructions. But we will step by step to get there. Okay. So any other question? So let me take a picture. And so many people today. Thank you very much.
Seria,